Right, so hi, I'm Fred. I work for a company called Dressipi, and one of the things that we do is build recommendation systems for clothing retailers. And there's kind of two things I want to talk to you about today, two problems that we had and that we solved and how we solved them. So one of them is a performance problem and the second was a memory problem. So part one, the following events happen in real time. So this isn't a reference to the TV show 24, showing my age a bit with my cultural references. This is about our real-time recommender. So when you build recommender systems, there is very often a tension between the things that you can do fast, but not so accurately, and the things that you can do accurately, but not fast. So the first part of this is your batch prediction. So typically this is running an algorithm that is quite accurate, but you have to run over all your data. And so it's quite slow. It's the sort of thing that maybe you can only do once or twice a day. And then you have your real-time predictions, which typically you have some sort of event stream coming in. So that's people clicking on things or people buying things, people watching videos, whatever real-time activity you have from your users. And you get some sort of real-time predictions out of those. And often this is a much simpler algorithm or one that runs on less data. And obviously we're greedy. We don't want to have to choose between these two things. We want to have both of them. So you combine both your batch predictions and your real-time predictions. Sometimes people call this a batch layer and a speedy layer. So this is a very, very common pattern that we decided to implement as well. So where did it go wrong? Well, everything was fine until we deployed to production. So until that point, everything was great. We had some great specs. We had a good PR. We tested it a lot in our staging environments. We also tested in, we have a sort of an offline environment where we simulate the improvement on the quality of the recommendations. I mean, everything looked great. I mean, in fact, we deployed it one morning and it was still fine. It was fine all the way throughout the day. And then the evening after we deployed it, this happened. So the blue line is the number of jobs in a queue, so the side of this backlog, which as you can see about 7 o'clock in the evening starts going up and up and up and up. The red line is the number of servers processing that queue. So you can see we start adding new servers to try and keep control of the backlog, but it doesn't really help. And yeah, it does kind of fix itself around 10 or 11 p.m. That wasn't us fixing something or turning it off. Most of the work that we do is e-commerce, and just enough customers, stopped shopping at that point in time. So the one good thing about this is that we had a real-time system if you have a real-time system and you have a backlog like that, it's not a real-time system anymore. But the good thing is that we had a real-time system whose failure mode was a non-real-time system, and our customers didn't know that we were deploying this new real-time recommender. So though we were kind of panicked about this, from the customer point of view, everything was still fine. Obviously, we really wanted to fix this. So the next day we came in monitoring to find out which job was responsible. We kind of had quite a good idea given what we just deployed. And it was this job, which is basically the same thing as the slide we had a few slides back. We had the batch predictions that we compute and store in a data store. We have real-time predictions that come out of an API. We combine these, we serialize them in a specific format, and we store them in a new place. And just looking at this, any of these components could be slow. Maybe we're hammering that data store, either reading the predictions or writing the updated real-time ones. Or maybe the real-time API is really slow. So had a closer look in our monitoring. So this is a screenshot from AppSignal, which is much like Skylight and New Relic and so on. Those two bits I've highlighted in red, those are all the data store accesses in the API calls. So as you can see, those are very, very small and not a problem. And the issue is this much bigger bit, which is 90–95% of the job runtime. And that corresponds to the serialized step from the previous slide. So luckily the code for that is relatively simple. We can have a quick look. We have this class called scoreMap, which conceptually contains a hash, which represent where the keys are the IDs of the items and the values are how recommended those items are. And the main entry point of this class from the outside world is the serialize method, which says turn yourself into a string of bytes. And it does that by turning itself into an array of integers, and then it uses pack to turn it into raw data. This toInt array method is relatively simple. All it's doing beyond flat map is we want to scale all the values so that they're always in the same range, which makes things much easier later on down the line. So we divide all the values through by a scale factor, which we compute down here, which is basically designed so that whatever initial values you have in your scores, what comes out of the serialization will always be between 0 and 1000, which just makes things easier to compare, easier to work with. So I looked at this for a while, spent a few minutes thinking, I wonder what's going on, and I couldn't figure out, nothing was jumping out at me yet. This must be the problem. So I decided to use a tool called ruby-prof. So ruby-prof is a profiler, and what that means is that you run your code inside ruby-prof, it records a bunch of data about what your code is doing, and then it gives you that output on where your code is spending time, what it's been doing. And just to be clear, it's not a replacement for New Relic or Skylight or something. It's something you use to analyze problems. It's not really something you run ahead of time unless you knew something was going to be slow. So we can have a quick look at my little ruby-prof benchmarking script. So start off, obviously require ruby-prof, it's a gem. I load some example data. Sometimes this is almost the hardest part of the problem. Maybe your performance problem is exhibited by a particularly pathologic type of data or certain patterns that you need to recreate to trigger the problem. I was lucky that this wasn't the case here, and it's really 500 randomly generated key value pair hash was enough to show the problem. This is where we actually do the profiling. So you can invoke ruby-prof in multiple ways. I quite like this one, where you do ruby-prof.profile, and anything that's in the block will get measured. And at the end of this result will be a data structure that comes out of ruby-prof, which contains all the data it's recorded. So obviously then you need to format that in some way that's readable by a human or by an external tool. ruby-prof ships with a bunch of formatting tools. I quite like this graph HTML printer one, which produces an HTML file. So I ran that, and you get an output like this, which is like quite a wall of text and numbers, given that it came from code that fits on one slide. But we'll dive into it and we'll see it's not quite as scary as it looks. So every row in this table looks like this, and every row represents one method. In this case, it's kind of not quite a method. In this case, it represents the block that was passed to ruby-prof, which is why it's got this weird global no method name. On the left here, we've got some timing information. So on both in number of seconds or milliseconds, and in percentages of the total runtime. So the difference between total, self, and child is how much time does this method spend executing itself, and that's total. Self is how much it spend doing its bits, and then everything else, or child, is how much time does it spend executing stuff that is elsewhere in this table. So as you might expect, this first line is 100% of total by definition, but the self is very, very low because all it does is trigger my code. And over here you have some call stack information. So there's one call to this method, and it made one call to serialize and one call to class .new. So the next couple of rows in the table are quite similar in that the total time is very close to 100%. The self time is very close to 0. So in a sense, there's almost not much point looking at these methods yet, because all they're doing is calling other methods where the work is happening. And this is quite common. You very often have a few layers of wrapper code or things that just set things up before you get to the actual work. So what I normally do is I scroll down the table till I find the first entry where the self time is something non-trivial. And if I do that, I come across this row. So we've spent 46% of our time running array each, which is a bit weird. Clearly the problem isn't each itself. I'm not about to open a bug on the Ruby bug tracker saying that each is slow. But what it's done is it's taken me to the place where where the action is happening. And that's when you need to start looking at the context around you, that call stack, to see what's going on. And all these are hyperlinks, so I can click on enumeral max by to see who is calling enumeral max by. So I know enumeral max by called each, and each is calling abs. The thing that I did stand out to me here is I called float at nearly 250,000 times, which seems quite odd given that my input wasn't very big. Sometimes ruby-prof will take you straight to the answer, and sometimes the thing that is the most valuable is that it will point out weird things like this. So always keep an eye out for stuff like a method being called way more times than you thought it would be, or I don't know, file open being called 1,000,000 times or something. So if I click around, if I follow these links a bit, now I'm trying to go back up the stack because I'm not really expecting there to be a problem in these methods that I can actually fix. So I need to go up the stack to find code that I've written and which I can fix. And if I do that, I get to this scale factor method, which is been called just under 500 times. And it's responsible for all those calls to max by, which then call each, which then call float all those millions of times. So if we have another look at that method, so it's taking the hash of scores, it's getting their values, and then it's going to have to iterate over that with max by to get the biggest value in the array. So it's going to call that block 500 times, but then I'm calling scale factor once for every value in the array. So I guess it doesn't make sense that that block is going to be executed 500 times 500 times, which is a very big number, so a quadratic in the input size. And that's why it's so slow. And the other thing is obviously it's returning the same value every single time because I'm not changing the @scores instance variable while I'm doing this. So that means that there's a very easy way to fix this, which is to just memorize scale factor. So we did this, and yeah, we deployed it several hundred times faster. So you might think, what's the downside to this? I can get all this insight into my code. Why would I not just have this running all the time so that whenever there's a problem, I can just click on it and get this extra data? And the big thing is that it slows down your code. The most recent ruby-prof version 1.0 is a lot better than it used to be, but you're still talking 3, 4, 5 times slower, depending on exactly on how your code is running, what your code is doing. So it's probably not a hit you can take in production. And that, of course, means you need to be able to reproduce the issue outside of the production environment, which, as I say, can be difficult. A corollary of this is that it distorts things. It's making your Ruby code 5 times slower, but it's not making database queries run slower. It's not making API calls or file I/O run much slower. So it will change the balance between the Ruby code and these other things, and it will tend to exaggerate the importance of the Ruby code. So even with those caveats, it's still a very useful tool. But you might be a bit greedy like me and thinking, well, can I get similar insights without these costs? And of course, the reason why ruby-prof has this large overhead is that ruby-prof is exact. It's measuring every single time you make a method call. ruby-prof has to record the call stack and update all these counters. And obviously, you're making a lot of method calls, so that overhead really, really adds up. Is there a way of getting similar insight without doing quite as much work and therefore quite as much overhead? And it turns out you can with a thing called a sampling profiler. What a sampling profiler does is it runs your code, it will stop your code periodically, maybe once a millisecond, and then so it's sampling the call stack. So every time it stops the code, it will say, well, what is the name of the currently running method, or what is the current call stack like? And very crudely, if you stop the code 1,000 times and 600 of those times it was method A, that was the current method, then at the end you would say, well, I think this code was spent 60% of its time running method A. And the cool thing is that you have this natural trade-off between accuracy and overhead. If I stop my code once a millisecond, that's a certain amount of overhead and a certain amount of accuracy. If I stop my code 100,000 times a second, then I'll have a lot more overhead, but I'll have some more accuracy. Or if I stop my code and monitor it 10 times a second, then I'll have a lot less accuracy, because I won't really see things to take less than a tenth of a second to run, but I'll have almost no overhead. There is a sampling profiler for Ruby. It's called stackprof. So it's relatively simple to run. You do stackprof.run. There are some options that you can look up in the documentation. And then in the block, you say what it is that you want to measure. The output from stackprof looks a bit like this. So it's a lot less rich than what you would get from ruby-prof. It has still kind of found the main culprit here, scale factor. It's maybe not giving the same amount of detail, but it's taking you to the point where the problem is, and then hopefully you can figure it out on its own. Or maybe it's now reduced the problem to something small enough that you can run ruby-prof on it. And it does have various output options for, you can do flame graphs or focus on specific methods and so on. So kind of the promise I made to you is that with a sampling profiler, I'd get less overhead. So I thought I'd put that to the test. And what I did is I took my benchmarking, my ruby-prof script from before, and I just changed it so that it ran it in a loop about 10 times. If I did it with no profiling or measuring of any sort, it took 6 seconds to run. When I ran it through ruby-prof, it took 27 seconds, so I'm getting that kind of 4 to 5 times slowdown. And when I ran it on stackprof with its default settings, which is stopping to measure once every millisecond, I got 6 seconds, and maybe, I mean, the difference between those two is a measurement error, right? It has almost no overhead. So this is something that I think you should feel comfortable running in production if you need it. And in fact, stackprof does ship with a middleware so that you can do that if you're running Rails or rack applications. So just to kind of wrap up on that first part, none of what I've talked about is about how you detect problems. So use monitoring, use users complaining on Twitter. That's how you can detect problems. Stackprof is really good for refining if you really need to get extra insight in production. But very often you can kind of skip that step. Extract a problem to a small benchmark. And again, this is not critical, but your life will be so much easier if you have this one script that does exactly the slow bit and nothing else, and you can just iterate on really quickly. And then use ruby-prof to drill into where the problem is happening and try and fix it. And then obviously the last step is always profit. So moving on to part 2, memory. I remember being a new Ruby developer. So I was a C developer before I learned Ruby. So one of my reactions when I came to Ruby, apart from just how much more expressive and amazing the language was wow, I never have to worry about memory again. Garbage collection would take care of all the memory, and the Ruby core team, they worry about memory for me. And it's certainly true that the Ruby core team spent a lot of time on that. This is just some of the improvements they've made to garbage collection Ruby over the past few years. I mean, that's not even counting just making it faster. But obviously, and maybe you're still in that honeymoon period, but I hate to break it to you, pretty soon as a Ruby developer, you will realize that, you still have to worry about memory. And getting memory wrong will cost you in different ways. If you take a huge file and load it into memory in one go, instead of loading it line by line or one chunk at a time, then that will have a big impact. If you are very wasteful with your memory and have loads of dependencies and loads of other things taking up memory, maybe that won't slow you down, but it could impact your running costs because it would change how many instances of your application you can run with a given amount of memory. If you do lots of allocations, lots of garbage collection, then that will also have a performance impact. I don't really want to talk about that kind of problem very much because in a way that is a performance problem like the one we dealt with before. The only difference is that instead of the metric being number of seconds it takes to execute, the metric is, well, how many allocations or how many bytes of memory did you allocate? And in fact, ruby-prof has a mode where we do exactly that. You just tell it, I don't want to measure time, I want to measure memory. And you'll get all those same charts and tables again, but with the costs being how much memory did this method allocate, how much memory did its children method allocate. And you can drill into that in exactly the same way. The story I want to tell is about an error we got through our monitoring system one day. So I got a page and it said, no memory error, failed to allocate, which is a bit weird. I'd seen that kind of just at the Rails console when I've done something stupid before. I've never seen it from a monitoring system, I guess because it takes quite a special combination of circumstances to run out of memory, but still have enough memory to be able to make an API call to a remote server to tell that server that you're out of memory. So, I thought I should probably have a look at this. I took a look at our monitoring. It wasn't a busy time of day. It was about, I think, 10 or 11 in the morning, which is a quiet time for us. Traffic was normal. Nothing weird was happening. So I kind of looked at some of our memory usage graphs. When you do that, what you're hoping to see is something like this. When the application starts up, it starts from low, it builds up very, very quickly, it just kind of levels off and flattens out. But what I saw was more like this green line where it never levels out. It just keeps growing and growing and growing. And when that happens, that means you have a memory leak, which I put in extra big text, extra big fonts, because memory leaks have always been a little bit scary. They were scary in the C world, and they're still scary in the Ruby world. How can this happen if Ruby is supposed to be freeing my memory for me? It's almost a betrayal. So where do they come from? Well, first off, C code. So if you have native extensions, those can just leak memory like any unmanaged native code. And how to find those is a big subject and a whole other talk. Other than that, and assuming there's not a bug in Ruby, which does also happen, if Ruby isn't garbage collecting your memory, it means that it thinks you're still using it. So it's some long-lived object, a cache, a global variable, something like that. So a lot of the time, a memory leak in Ruby boils down to misunderstood or not understanding object life cycles. And I'll show what I mean by that with an example. So many years ago, I wrote this rack middleware, which I copied over some of the code in here from a Rails application. In particular, this little sort of very small cache, where I'd cache in memory some of these active record objects, and it was just a little view helper that seemed quite harmless at the time. And in a Rails controller or a Rails helper, this is absolutely fine, because there's a key difference between a Rails controller and a rack middleware, which is in a Rails controller, every single request is a new instance of the controller. So this @things instance variable was lasting 50 milliseconds, 100 milliseconds, and it would accumulate 5, 10, maybe 20 objects, and then it would get the controller gets released, and all this memory gets freed as well. A rack middleware is completely different. A rack middleware, there's one instance for the entire application, and it never gets destroyed as long as the application is running. So this @things instance variable, this hash, was just growing and growing and growing. And in fact, if you leave it running long enough, you'll probably have the entirety of that table cached in memory, which is obviously a very bad thing, even if in-memory databases are a good thing in other cases. And just more generally, I think the reason why leaks are scary is because they're a global problem. It's not like a performance problem where you'll have your monitor saying this action is slow, or a user telling you the app gets really slow when I do this one thing. You don't really have somewhere to start. You just have one number, memory usage, and it's going up. And that doesn't really tell you where to start looking. Memory usage is complicated and noisy as well. It's not the case that every single request should have a net memory impact of 0, for example. There are caches, there are threads doing stuff in the same process at the same time. It's very common for code to only load the things that it needs the first time it runs. So if you have a big table of data that you need for, Unicode conversions, you probably only load that data the first time it's accessed. And then it's also very easily hidden in a dependency. It's very easy to introduce memory leaks, and so it's very easy for third parties to have them. So there is this tool called bundler leak, which is quite useful. It's not doing anything super clever. It's just a public database of versions of gems that are known to leak. But you can run that over your gem files or lock, and it will tell you if you're using banned versions. And kind of fundamentally, the problem, it really is a needle in a haystack type problem. You're looking for one small bit of code that's bad in your entire application. And if one request allocates maybe a few megabytes of memory, it's probably only leaking a few hundred bytes or a few kilobytes, a tiny proportion of the overall memory usage. So let's get back to my problem. So I've got a Rails app. It's got memory usage that grows slowly but surely. So my first thought was, well, I can't easily find out where this is happening, but maybe I can find out when it's happening. Because my monitoring can't tell me where the leaking code is, but if it can tell me it's been happening since last Tuesday, then that makes things much easier. I can just look at only the changes that we've made since then. So I had another look, and the answer I was hoping for was, it's been happening since the last deploy or for the last 3 deploys or something. Unfortunately, the answer was at least a year. And at least a year because we had 1 year's worth of monitoring data. So you might think, how on earth can you have a memory leak like this for a year and not notice? There's a couple of reasons. The first is it's either a slow leak or a very rare leak. So we don't run this application on a very big instance. It has 4 gigs of memory. It gets 3 million requests a day, and it still takes it 2 weeks for the application to kind of get low on memory. And the simple truth is that we restart the application much more often than every 2 weeks. We deploy much more than that. Even if we're not deploying that application, if we don't have any changes for it, we scale it up when it's busy, we scale it down when it's quiet. So it's very rare for an instance of the application to be running long enough for the leak to be a problem. In the very rare cases where it is a problem and an instance runs out of memory and dies, well, it gets automatically detected as unhealthy, it gets removed from the load balancer, and a new instance gets started automatically. And it just becomes another anecdote when I blame AWS and say that their servers are rubbish. So in a way, this memory leak was not a problem. This is fine. So thank you for coming to my talk. Seriously, there is some merit to the let it crash argument, but I really wanted to fix this leak. The problem I had was that I couldn't reproduce it on my development machine. I spent a good afternoon trying various tools to generate artificial load against it, of various types and various other memory tools for Ruby. I wasn't getting anywhere. Whenever I did, the code was not leaking, or it was leaking so slowly that I couldn't see it. So what could be happening? Like maybe I was just not hitting the right URL. I tried a couple of URLs, the ones I thought that were the most obvious, but if you remember, I don't know if this is a slow leak or a rare leak. Maybe it's this URL that only gets hit once an hour, and every hour it leaks a megabyte. Maybe it's a usage pattern thing. Maybe the memory leak is triggered by a race condition or by a certain pattern of requests that I haven't managed to reproduce in my local testing. Or maybe it's some sort of environment difference. Which brings me to my next topic, which is, I guess, kind of a slightly a taboo word, which is debugging in production, which sounds very dirty. We shouldn't be doing it. But sometimes it is the best place. And to be clear, I don't mean, kind of old school, I'm going to open up a text editor on the server and start editing my application in real time. I mean, adding some instrumentation to my code to get a little bit of extra insight. And just trying to get a little bit more understanding of what's happening. And there's 2 tools that I used to do this. So the first is rbtrace, which is an amazing tool from a chap called Aman Gupta, who is actually also the person who wrote stackprof, and allows you to peer into a running Ruby process. And that allows you to do a lot of things. So you can get kind of a fire hose of all the method calls that are being made when garbage collection is happening. You can dump backtraces. So for example, say you have a script that's sitting there consuming 100% CPU and you don't know what it's doing, or maybe it's consuming 0% CPU when it should be doing something. You can use rbtrace to get the backtrace from each thread in the process, and you can see what it's doing or not doing. But here we're going to use it for another ability, which is you can inject arbitrary Ruby into a process. The second thing we're going to be using is something that's actually part of Ruby itself, called trace object allocations. So it's from ObjectSpace. which has all kinds of weird things that you don't use that often. And what it does is that it records some details about every single memory allocation, broadly speaking, when it was allocated, where it was allocated, and what is it. And you gather all this data and they can dump it into a file that they call a heap dump. It does have this warning in the documentation, which is a little bit scary. Note, this feature introduces a huge performance decrease and a huge memory consumption, which, kind of makes sense given what it's doing, instrumenting every single allocation. But I still quite wanted to use this. So my plan was, well, this is an application that's deployed across many servers. So maybe if I only turn this on one server, and in fact, on that one server, on only one Ruby instance inside that server, and then use rbtrace to just turn it on just for a few minutes. And if I do it at a quiet time of day, then it's probably only going to have a very limited impact on our users. And then that is the extent of my debugging production. I'll get that heap dump file, I'll copy it back to my local machine, and do the analysis offline. There's one important point I want to make, is you might think, oh, this is all very easy and very obvious if you know about it. When I encountered this memory leak, I didn't actually know about it. I had to Google this. So there's no shame in that. So let's actually get going with the actual debugging. So it looks a bit like this. Bundle exec rbtrace is kind of this incantation that you have to have. The bit we're actually trying to do is get it to run ObjectSpace.trace object allocation start. So tell ObjectSpace to start recording this data. You can get a heap dump without doing this, but you'll be missing a lot of the interesting data. So after that was been running for a few minutes, I use rbtrace again to execute this code. So do some run garbage collection and then open a file and dump all that data into my heap dump. And then obviously don't forget to stop object allocation tracing. So I do this. I had a file with a couple of 100 megabytes, and then you've got to start looking at it. So now what is in a heap dump? It's basically one JSON object per line, and each one of those JSON objects represents one object from your Ruby application's heap. So you get an address. So this is literally just where in memory was this object. You get some type information. So this is not the Ruby type. It's not going to have your class names. This is kind of the internal C typing system. So there are about a dozen types, and it's things like object, class, string, symbol, array, hash. But a lot of things will just be called object. You do get this class. So this is the memory address of the class for this object. So if you're interested enough, you can grep through your heap dump to find that class object. A lot of the time you don't need to, because you can see this information, which is where was that memory allocated from. So in this case, it got allocated by the Mongo ID gem on line 335 of document.rb. So I know it's one of my Mongo ID objects. Generation, so this is very important. So every time garbage collection runs, generation increases by 1. And so what this allows you to know is kind of when was the memory allocated. Is this memory that's been allocated very recently and it's kind of fine that it's still here, or was this memory that was allocated a long time ago and should have been cleared up? And you get some information on the footprint of the object. So this one has 3 instance variables. Mem size, this corresponds to the ObjectSpace mem size of method. Kind of take it with a pinch of salt, especially if it says 40, because 40 is kind of the default size for any Ruby object. So sometimes useful. I mean, with a string, it will tell you how long the string is, but not always so good. And then references. So this is more especially interesting if you've got some kind of circular memory loop type thing. But it's all the other Ruby objects this thing was holding on to. So if you had an array, for example, then references will be a list of the objects in the array. And then last of all, you have this flags hash, which has just some extra information about the object. So in this case, WB protected refers to the incremental garbage collection that was added Ruby 2.3, I think. And this is just saying this is not an object that needs to be treated specially by that. So this is very interesting. It's very low-level data, but it's much too detailed, much too low-level to start your investigation. My heap dump had 1 million objects in it like this, and obviously you can't look at all that. You need some aggregate statistics, some kind of summary of this to help you find where the problem is. So I used a gem called Heap by Richard Schneeman for this. There are similar other tools around there, but I quite like this one. And basically you just give it a heap dump and it'll print out some data for it. So the first thing I did, just to kind of understand what I'd be looking at, is I took a heap dump from an application which I knew didn't have a memory leak. So I ran it, heap read, you give it a path to your dump, kind of whirs away, and then it starts printing out the output. So the first line is always generation nil, and what this means is that this is memory that was allocated before you turned on allocation tracing. So that's why the memory is 0 kilobytes here, because it just doesn't know. But that's fine. You know, this is memory that was allocated when it loaded your code. So, for example, all the Rails code, all your classes, and so on, that was allocated and has never been released. I get some more information here. So this is basically saying that we started recording detailed allocations around generation 61. We still have some of these objects around. Again, that's kind of fine. You know, it's very common now when an application starts up that it will be allocating memory that it doesn't legitimately need to keep for all time. And then we get this. So we go straight from generation 63 to generation 2222. This is great. What that means is that in between, there were 2,160 generations worth of memory, where the memory was allocated, it was used, and then it was released. And then we have a little bit of memory right at the end that's been allocated very recently and is still being used. And that's what you would like to see in an application. So then I ran this heap dump tool on my bad heap dump. The start of it looks very similar. I have this nil generation. I have some very early generations where I'm still holding on to memory. But then I never get this gap. You know, as I kept on scanning through this output, you see every single generation still has some objects that are still live, which is kind of the definition of a leak. So a good question would be, what are these objects? What do they look like? And you could obviously inspect the dump by hand, just grep for 1879, or Heap will do this for you. So if I do heap read heap.dump 1879, then it will show me some information about these things. The first thing it does is that it shows me the size of these objects and where they came from. So by memory, I've got 858 bytes that came from somewhere in Action View template, and a small number of bytes that came from somewhere in active support remove method. The next thing it shows me is the actual values themselves. So these strings here, and if you're familiar with Rails internals, then you'll recognize this as the name that Rails uses internally for templates when it compiles them. And even without that, you'd recognize this as kind of the name of a Rails template. And this was actually a really kind of a key moment for me, because for the first time, I actually had some idea of where in my application this leak was happening. Like, there was only one action in my app that renders this template. So I've shrunk the problem. Even if I didn't go any further with this tool, I've shrunk the problem from I have a whole Rails application that's leaking somewhere to I have one controller action that's leaking. So that's a pivotal moment for me. And then lastly, there was this flag information, which I had to go back to the heap dump for. So old, fair enough, but of course the interesting one is uncollectible true, which I guess maybe that explains why the memory is leaking, but it's uncollectible. But then that's just another question: what does uncollectible mean, and why is that happening? So from my heap dump work, I guess I had two questions. One is, why is the method name uncollectible? And why are there so many of them? I mean, I know ActiveView compiles the templates, but it's supposed to compile them once and then cache them. So I should only have as many of these weird symbols, or these weird names in my app as there are views. So, you know, a few hundred at most, not millions and millions of them. And I knew method names are symbols, and if you're a long-term Ruby developer, you may remember that symbols have been the root of many memory problems in the past, of denial of service type problems, because it used to be that you could not garbage collect a symbol. But one of the changes in Ruby 2.2 was symbols can be garbage collected. So what's happening here? I read in a little bit more about symbol garbage collection, and it turns out terms and conditions may apply. Although there is one class, you know, symbol, and they all look the same from the Ruby world, there are actually two kinds of symbols. There are Immortal symbols. These are, roughly speaking, symbols corrected directly from Ruby. So if you call foo.toSym, you'll get an Immortal symbol. The other kind of symbol is an Immortal symbol, and this happens from C-level references. So there's a method inside the Ruby C API called rbintern, which creates these. And the short version is that Immortal symbols can't be garbage collected. Immortal symbols can be. And defining a method creates an Immortal symbol. So that's where the memory leak comes from. And actually, this is kind of a general pattern in garbage collection problems in Ruby. There's always the C code that makes things complicated. So that's a problem that's kind of solved in the sense that this is not something I could fix. ActionView defines methods. Methods cause Immortal symbols to be allocated. Those symbols aren't going away. Nothing I can do about that. I'm still left with a second problem. Why are there so many methods? There's supposed to be a template cache. So I thought I should probably find out about template caching, because all I kind of knew before that was templates get compiled into a method and it picks a random name each time. And actually my first thought was I should probably check that template caching is actually turned on. Like, it's very easy to accidentally turn this off when you're investigating a problem and forget to turn it back on, but it was on. So I did some reading around the Rails code base. I found this. So each template is compiled to a method with a random name. Each entry in the view search path is an object called a resolver. And a resolver is a thing that either returns a compiled template from cache or loads from disk. So I had thought before that the Rails template cache was like one big hash, but it's not. It's one big one hash or one cache for every entry in the search path. So that got me thinking about search paths and view paths. And I found this bit of code in my app, which has a bit of history in it. So this view is something that our clients embed in their sites with an iframe. And historically, we were embedded in their desktop site. And then they did a mobile first redesign of their site. So we redesigned our embed. And they wanted to run the two sites in parallel. So we said, okay, if you pass us this query parameter, we'll detect that you want to embed the new version. And if so, we'll do this. So our mobile version had the same controller code and most of the same views. We just had some view overrides that we were activating with prepend view path. So if you think about what happens normally is your app starts up. Each entry in the search path is a cache and is empty. So I got the app/views. I got some views from the devise gem, and the app is just booted, so everything is empty. Run some requests, and the caches start filling up. But then we get to a stable state where whenever you're rendering a view, it's probably a view we've already used. So what happens the first time a request for the mobile variant comes in? Well, we push this new entry into the search path. So here it is, it's empty, it's never been used. This action renders a few templates, and there's stuff in the cache. But that prepend view path was a per action override. I just did it in my before action callback. So at the end of the request, it gets removed from the view path. And then the next time a mobile request comes in, it kind of starts again with a fresh resolver, a fresh cache. So I've got this caching system, which in this particular set of circumstances is producing a new empty sync cache on every single request. So this is also kind of a lifecycle misunderstanding. Because every template is always compiled with a random name, which means that every request leaks a symbol. Luckily for us, by the time we noticed this, supporting these two versions was actually obsolete. So we just got rid of the desktop views, moved everything into one folder, deployed. This was our memory usage before we found the problem. And the black line is where we deployed it. And you see afterwards, it's kind of flat. So fixed our problem. So just kind of summarize on that. I would say, first of all, like, don't be afraid of production. Like sometimes that's where you need to go to get the extra information. You know, obviously with great power comes great responsibility, but you know it can be done safely. Then the big takeaway really is heap dumps have a tremendous amount of information about what your application is doing from memory. And yeah, pay attention to life cycles. Objects live a long time when you think they are short-lived or a problem. Objects that have a short lifetime that you thought were very long can also be a problem. So, you know, I experienced both. And yeah, thank you. That's it. There's some further reading for anyone who's interested.
Thank you, Frederick. That was a very interesting and nice presentation, and definitely I myself learned something from it, and I hope yeah, all the other attendees have also learned something. We are unfortunately running a little bit out of time, so I'm not sure if we will be able to go into the question and answer section right now, but I think that you can open the question and answer section and answer the questions in there. And now I think that we will move to the next speech for today. But thank you very much.
Thank you.